Okay, thanks, Matt. Can everyone see my screen okay? Yes.
Yep.
Uh, okay, sorry, didn't sharing screen. I can't see people right now. Yeah, so we're going to talk about RE Bench today, which is a benchmark for evaluating AI's ability to assist in AI research and development. But before I talk about that, I want to talk a little bit about the this kind of general idea of recursive self-improvement, which Matt alluded to. This has been our theme basically for the last few weeks and a few weeks past this. So a lot of the papers that we've been talking about all kind of relate to this, but we haven't really talked about it in detail, just as a separate idea. So I wanted to do that because this is really an important idea. It's critical for this paper, but also, for the rest, like I said, what we've been reading, what we're going to read. And also it's just a really important idea, I think most important ideas in AI safety in general. Um, so if you imagine, um, just any kind of technological improvement process, you can kind of think of it as having these three aspects where, you do some research, you develop that into something useful, and then you deploy it, you present it, you launch it, whatever it is. So this could be software development lifecycle, but it could be any kind of technology. And then it's circular because, after you deploy it, then you start to work on the next version. So, you could have a V1, it's just one trip around the circle, V2, V3, whatever. And so the process is kind of continual improvement. You have this overall technology just kind of keeps getting better and better. But what's important for our purposes is that, these circles, this, one cycle of developing one version of a technology, um, there's no reason to think that they are getting uh, faster or shorter or smaller, basically. The V1 may take longer than the V2 or may take less time. It just depends on, the features and how much resources you put into it and, specifically the technology state it's in, whatever. Um, but basically it's overall kind of a linear process where things are getting better in a kind of constant way. Um, and that's a general way that things have been developed in most technologies. And it's also been how AI has been developed pretty much up till now. The last few years it's been very fast, but it hasn't been accelerating. Um, but I think that's starting to change. So if you imagine a slightly different model where the AI that you're building is able to make your research and development steps faster, then it looks a little different. So, it may start the same, you do research and development, and then you deploy something, but if that deployment can then help your research and development efforts and make them go faster, then the next trip around is going to be uh, quicker, and then that's going to make things even faster the next time because you're going to have another even better AI to assist you. And so, it looks like this kind of feedback loop where you're going faster and faster and faster. Um, and uh, in this example here, where AI is just kind of helping, there is a limit to how fast it can go because you still have humans in the loop. But in theory, you could imagine a fully autonomous research and development cycle that is limited only by the speed of computer thought, where it just gets faster and faster and faster, and that's basically the speed of light. Um, and so this is something, it's people call it an intelligence explosion, um, but it's something that people have talked about for a long time as just a theory or a possibility that something might happen, but it's actually is just starting to happen. If you have been following, the news with, like, for example, Claude 4.6 came out just 2 months after Claude 4.5, and according to Anthropic, it was 100% of the lines of code in Claude 4.6 were written by Claude. That doesn't mean there weren't humans in the loop. So, we're not in this fully autonomous cycle yet, but we are definitely in a cycle where things are starting to speed up. And that may continue. Things may continue to speed up. Um, so they talk about this in the paper as well, and that motivates what they're doing. But so I wanted to, we'll get into that in a second, but I wanted to just stop here for a second because I've just spent a little bit of time on this, but I think it is a really important idea. So are there any questions or anything about this before I move on? Okay.
It's maybe
Hopefully
not
everyone.
pertinent to the paper exactly, but I guess it's worth, since you've brought us to this kind of more general topic. People often make a distinction. I don't know if you're familiar with like software based intelligence explosion and hardware based one. Are you familiar with this? Maybe you could speak to it for a minute.
I'm not familiar with that actually, so maybe you could
Sure,
speak
yeah.
to
I
it.
mean, I'm not an expert either, so for what it's worth, people talk about like the ability for the topic of this paper is like models able to improve say like the efficiency of their kernel where a GPU runs so you can get more for a fixed amount of compute you could I guess if I understand it correctly you could get more um, training passes, more tokens trained on for the same fixed amount of compute. Um, but so that would be like it improving its own software, right? But you could also imagine that it's able to build better chips. It could help design chips for a future iteration that are physically different. That's
Right,
like the software versus the hardware distinction. But you could imagine it going all the way up and down that that's where sort of the distinction is the most narrow. But like you could imagine, hardware based could be also like improving the efficiency of the air circulation of the data center, right? Might plausibly be part of the hardware stack,
right.
so to speak. Similarly, the software might be something as good as just like improving I don't know, interface with a user for the collection of data or something like that. It might be like, something about the software. Anyways, that's the distinction as I understand it, but I'm no expert.
Yeah, yeah. I mean, that makes sense. I think that's a larger point there is there could be lots of different ways that an AI could assist or could improve its own research and development. And they could all kind of be mixed in here as well. And especially with the AIs that we have now, where they're pretty general, then we don't really know in what ways this could happen. Um, okay, so let's move on to the paper and its kind of application of this. So the authors of the paper talk about this as a risk basically, and they're particularly concerned about the risks of fully autonomous development. And when you have that speed up that just keeps going and going very easily, capability could overwhelm your safety measures. If the AI is kind of developing its own code at a frontier lab, then it sort of has more opportunities for um, sabotaging. If it's misaligned, it can make the next generation of AI misaligned. And then, if the model weights get stolen, then it just kind of makes the other risks more dire if a model can get stolen and it can develop other models. Um, so the conclusion they come to is that we need an early warning evaluation. And that's really what motivates them to create this benchmark. So the idea is that, we would test AIs on this benchmark, and when when they did well on the benchmark, then we would sort of have a warning that this intelligent explosion could be coming soon. And so they then ask the question, okay, what makes for good early warning evaluation? And they come up with three things. So one is feasibility. So just a metric or a benchmark that has clear instructions, no technical blocking issues. I actually would have thought this kind of goes without saying for any benchmark, but apparently that's not true. According to them anyway, the benchmarks often have problems with this. Um, Ecological validity obviously has to correlate with the ability to do real world R&D, and resistance to saturation. So saturation is probably a concept you're familiar with. It's, the idea is that if you have some kind of benchmark, you're scoring a computer from like 0 to 100. Once it gets better and better, once it hits 100, basically, then the benchmark is no longer useful because it doesn't really tell you anything because anything beyond that AI is going to be able to do that. So that is a very common problem with benchmarks over the past few years that people come up with these and expect them to be, useful for much longer than they are, but the AIs just kind of blow past them. So that's something that they don't. It's not possible to create a benchmark that's immune to saturation, but they want to create one that will be resistant to it as long as possible. So basically hard tasks. Um, so they also kind of compare this to existing benchmarks. There's a lot of detail here we don't really need to worry about, but the important um, issue here is that you can see RE benches being positioned as like a much longer time horizon than any other benchmark. So 8 hours versus at most 30 minutes for the others. So it's again that resistance to saturation, like a really hard task, which we know longer tests tend to be harder for LLMs. And the trade-off, of course, is that there are many fewer tasks on this benchmark than on other benchmarks. Um, okay, so that's background. Any questions about background before I move on to methodology, what exactly they did? Um, okay, so they started again with these things they're aiming for in this benchmark: feasible, ecological valid, saturation resistant. And that informed their design pillars. So they wanted to get coverage from a lot of different areas of AI research and development, have steady progress and a high ceiling. They had some practical considerations, limited compute and can't get experts for longer than 8 hours is the uh, constraint they had there. So based on that, they went through this creation process, and it's actually, pretty elaborate, going through multiple technical reviews. They come up with ideas. They sort of narrow them down. Get after they get these expert baselines, they end up with seven tasks, and all of these seven tasks kind of work the same way. They're all 8 hours long for the human baseliner. They have this environment where they have the instructions of the task. They have these data sets that you can use. Every task has a starting solution. And then, the agent or the human works in this environment. They can edit files, run code, um, and then they can also submit their solution for scoring as often as they want to. And the scoring solution, except for one task where they kind of hold off the score because there's like a test set and a validation set. Um, the solution is the score is generally shared with the agent or the human working on this, so they can kind of do this and get feedback basically on their solution and continue to iterate on it, make it better. Um, and here are the tasks. So there's a variety of different tasks in terms of the skills required, the parts of the pipeline. Some of the tasks are harder than others. Again, they're all designed to take um, more than 8 hours in the sense that they don't want the human developers to get like a complete solution or to get as best a solution as they can have in that 8 hours. They want it to have this really high ceiling. Um, and the way they scored this is they had the starting solution for all of them, which they set to 0. And any solution that scored worse than the starting solution was also set to a score of 0. Um, and they had a reference solution for all of these, which they set to a score of 1. This was not a ceiling though, because it is possible for the AIs and the humans to do better than the reference solution. That was true in some of the tests they had. So the score could be higher than 1. And they use this best of K scoring, which we'll talk about more when we get to the results. But basically, the way they tended to score things is, over a given period of time, they would look at all of the solutions submitted and then take the best one to get a score. Um, so so that did well. We get to the implications of that in a while, but that's what they did. There are multiple scores, and the best one was the one that counted. Um, so in terms of other things about the methodology here, there were 2 agents, and which were state of the art at that time. They're kind of a little bit behind now. Um, 2 scaffolds, which are pretty, I guess, normal scaffolds. I don't know too much about that, but that's according to what they say. Um, Pretty standard. And then for the humans, they had 3 different source pools from they got humans from. So they had you could tell the different source pools that actually had very different scores, so had very different humans, which is important because not every human worked on every task. So they had 61 humans, and then total runs is 71. A run is basically one human working on one task for 8 hours. So most of their human baseliners only did one task. Um, and they did allow them to use LLMs and browse the internet for this task, which I thought was kind of an interesting choice. Okay, so yeah, that's it for methodology. I'll stop here again for questions. Any questions? Okay, so let's move on to results. So this is the headline result. It's basically that the agents did better at short time periods. So up to 2 hours, the agent solutions were better. But for longer time periods, 8 hours, just the total amount of time that the humans worked, the humans beat the agents. And this is something that held up kind of across tasks and across different agents and scaffolds and so on. And again, the sort of scores are a little bit weird here because they're, for example, all the humans did all the tasks for 8 hours. So, this data point is actually humans doing tasks for 8 hours. The other data points are kind of, interpolated or, for example, a 16-hour data point for human would be, they take 2 humans and then they take the best of those 2 human scores across that entire 16 hours of both of their attempts. And same thing for 32 and 64, and this is true for the agent measurements as well. And then the human measurement, so like 2 hours here. It's not actually a person trying to get the best solution in 2 hours. It's just like the first 2 hours basically of a human's effort. Um, and here's the results by task. You can see there's a lot of variation by task, even though they did try to normalize the scores. Um, overall, you can see humans doing better. Uh, this is for 32 hours, 32-hour mark. But for some tasks, humans did a lot better, and for a couple tasks, agents did almost or even one case as well as humans. Um, but there's a lot of caveats with drawing these kinds of cross-task comparisons in particular. Because again, these are normalized scores, but that's based on the reference solution, and so different reference solutions would get you different looking graph here. You have different humans doing different tasks, and some of the humans were better than others. So you can't really say humans did kind of better on this task than others. You can't say humans in general did that. And then because they did this kind of best of K scoring, that means that like if you guessed a lot, basically, and then there was just some randomness in the guessing, that actually could be an effective strategy for some performance on some tasks. And they mention one task in particular where this is true. And that is relevant for comparing human and uh, agent performance because agents did that strategy a lot more. They basically guessed or they submitted a lot more strategies, which we'll get to next. Um, so yeah, as I mentioned here, uh, 25 to 37 scores per hour and agents submitted and versus 3 to 4 for humans. So they basically agents tried lots of things starting from the very, very beginning. Um, Agents also tended to kind of stick with the starting solution and just do like a bunch of different tweaks to it. So their solutions were in general not as creative, although oftentimes that was an effective solution. But humans tended to work differently. They tended to try novel approaches that hadn't been shown in the starting solution. Um, and just to restate the main result here, the agents really struggled to work over a long period of time and to build on the work that they had done before. So there was one particular result where basically if you wiped the agent's um, context every 30 minutes, then that was you got better results than if you allowed it to just continue working. So all that accumulated context was actually degrading performance. It was just confusing the model. Whereas that worked very differently for humans. For humans, they would build on their previous work and kind of gradually get better over time. So they do some kind of a little bit speculative analysis of what are the possible task characteristics that would make an AI do relatively better than a human. But with only 7 tests, again, you have to take this with a lot of big grain of salt. But some of the possibilities they talk about are, very short and high fidelity feedback loops. If you can know how you're doing very quickly and easily, that can benefit agents. If there's specialized expertise that's needed, agents are more likely to know that because they just have a kind of broader set of knowledge than humans. Um, Tasks with few surprises and not much need for exploration or discovery, or basically low engineering complexity. And this last one is actually the only one that they have some indication in the data that is true. So they do this graph of on the y-axis is the agent human gap, where basically the agent higher means the agents did better. And then on the x-axis is just lines of code. And this is a nice looking graph, but again, with only 7 tasks here, and the tasks are different in more than just the way of, lines of code, engineering complexity. They're different in lots of ways. This is really, again, just kind of speculative. Seven data points are not going to be actually statistically significant. Um, okay, so that's it about results. I just have one more thing, one more slide, which is about the discussion. But any questions about specifically what they found? Okay, so let's move on to the discussion. So in the paper, they spend most of the discussion section talking about whether performance on RE bench overestimates or underestimates kind of real world ability of AIs to do research and development, AI research and development. And they kind of give arguments on both sides. So this idea of overestimation would be if, an agent could do really well on RE bench, but they wouldn't really be able to assist meaningfully in AI R&D. And the argument for that is just that in the real world, the tasks are much more complex. So on a bunch of different dimensions here, the time horizon of the task, the feedback loops, lines of code, other things going on, and objectives and scoring, clarity, all that. Real world R&D is just much more complex, and so there's a question whether this really might overestimate performance on real world tasks. Um, but then the other side, there are arguments why it might underestimate performance or ability for AIs to do real world R&D. One argument for that is cost. So they talk about this a lot, where in this case for their study, there was about a 15x difference in the compute cost for the agents versus how much they had to pay the human baseliners to do these tasks. So even if an agent was, 1/10 as productive as a human, then it might still be cost effective, for example, to have them assist in AI R&D. The scaffolding could be optimized, so they just used kind of standard scaffolds, whereas you might be able to come up with some scaffolding that worked better. Um, Agents might use different workflows. So instead of just plugging in an AI agent into a human workflow like they did in this test, maybe there's different ways of doing AI R&D that agents would be better at. And then the final one is partial versus full automation. And this is not one that they actually talk about in this section, but it is something that I think is really important to think about with regard to this paper, and actually, for me, affects how I think about it in general. Because like I said before, they're kind of most worried about full automation, and they position this as like a early warning system for full automation. And the reason they give is that, well, partial automation might make things faster, but there's still humans in the loop, so it's not it's as concerning if things getting out of control. Um, and that's true, but I also think that partial automation, even if AI is just assisting in the process, it does kind of trigger that accelerating feedback loop. So that once you have that going, and like I said, it's kind of already started. You have the development getting faster and faster. And then, at a certain point, full automation will be a lot more feasible. And so for me, that is kind of an important threshold, when we cross that. And like I said, we're kind of already crossing it, or maybe have crossed it, and we're just starting to do this. And and we know this because, not because the agents are succeeding on some particular benchmark. I don't know if you ran the latest agents through RE bench, they probably would not do, a ton better, probably not as well as humans still. Um, but the frontier labs themselves have told us, this is what they're doing, and it's being useful, and I think all the labs are doing this now. And so that's why, actually, even though I do like this paper a lot, and I think they've done a very good job, and they've been very careful about how they've gone about analyzing this, and I think it's useful data. I don't feel like it personally. I don't feel like it actually succeeds on its merits as an early warning system. In terms of how they position it as, like, okay, here's a metric, and if we test agents and they get high in this metric, then we should start being worried. Um, because I think that a better way to test whether AI R&D is feasible is just to sort of try it out, and that's what the labs are doing. And so this, I do think it can be useful in general to get a sense of what AI agents are good at in the AI R&D process versus what they're not, and maybe give us some sense of sort of how close we are to full automation. But in terms of just as a detector, I feel like that ship has sailed. We already the sirens should already be going off if that's if that's something we're worried about, because this process of speed up has already started. Um, all right, so that is all that I had. So we can, I think,